Hello, my fellow lazy chemists, and welcome to today's lecture, which is going to be on types of reactions, in particular organic reactions. And in this lecture, we're going to go ahead and talk about the two main subtypes of organic reactions, and we're also going to go ahead and talk about like the types that are in there as well, depending upon what happens to the molecule. The things that I'm going to want you to realize about this lecture is that this is primarily an information get out there lecture. In particular, that you guys are going to receive this information. The only information that I feel that you're going to need to interact and really understand and use a lot is the carbocation section, so make sure that you're paying attention to that part in particular. And then classifying reactions, this is just another set that's special to, in particular, organic chemistry. So the first type that we have to go ahead and look at is going to be homolytic versus heterolytic fusion. Okay. Sorry, and it's fission. Okay. And fission means that it's coming apart. And this is going to be the first one is homolytic. Homo, which means same. And if you notice our definition, a split between a bond in which atoms on opposite sides of the bond receive an electron. So essentially, they both get the same amount of electrons back. All right, and that's going to differ from heterolytic fusion in that the splitting of that bond, the atoms on opposite sides will not have an equal distribution of electrons, meaning that one will get the electron and the other will not. Okay. Here is an example of homolytic fusion, in particular between molecules A and B. You'll notice that there is a bond. And notice that when we have that fission, this should be fission here. When we have that fission, that they both have an electron. And this is an example here as well. Notice that we have the CH3 and the CH3, and we break that bond, and each one has that electron right there. They both have the same charge at the end, therefore it's homo-same. Heterolytic fusion is when we're going to go ahead and have a different case when we have one that's going to grab an electron and the other is not going to be taking an electron from that, which means that we're going to end up having different charges on the molecules here. The first example, we have the electron going over to the B molecule. Notice that it has become negatively charged because it grabbed both of the electrons. And then the A molecule will end up being positive. When the opposite happens, the A molecule will grab both the electrons and the B will become positive. This is an example here of how it can happen. Notice that the break comes between the carbon and the bromine. Okay. And in this case, since bromine is more electronegative than carbon, it's more likely to grab those electrons and it will have a negative charge where the carbon will be left with a positive charge. Okay. And again, in general, heterolytic fusion is going to happen more often when one of the molecules is going to be more electronegative. So if we have a big electronegativity difference, that's going to end up changing whether it's going to be heterolytic fusion or homolytic fusion. Okay. Next, so in this case, we have homolytic fission, and because they end up having the same kind of electronegativity, we'll end up getting these types of radicals formed. And when we have unbonded electrons, we typically like to call those radicals. And that's something that you guys may have heard in commercial, especially for commercials that are trying to advertise like acai berries or, you know, the next great free radical reducing trend. These are the kind of radicals that they're actually talking about. Now, most of those trends, you know, acai berries aren't going to do all that much. And, you know, when I was growing up, it was specifically tomatoes. So just be aware that that's what they're talking about. They're talking about atoms that end up, you know, having just all of their electrons. Okay. The next is that we're going to go ahead and have some terms here. The first term is going to be a free radical, okay? And this is an uncharged molecule, typically highly reactive and short-lived, having an unpaired valence electron, okay? And this literally means that it has usually one unpaired valence electron. It can also have two unpaired electrons in the case of oxygen. Oxygen is also considered a free radical when it's all by itself. But usually if it has at least one unpaired electron, it's a free radical. Next is going to be an initiation step. And this is something that you guys may be able to understand a little bit with the idea of activation energy. And this is usually the step where we add energy to this molecule. If you want to imagine, these two carbons here are at their lowest energy state when they're bonded. Therefore, in order to get them to break, we have to add energy to that process. So the initiation step is where we add energy to that particular process. The next is the propagation step. So typically, when we end up forming these free radicals, they will cause a chain reaction, in which case they will end up reacting with even more molecules and causing even more free radicals to form. And that's what will happen often with a propagation step, that we'll usually get it started with the initiation step. It'll propagate usually through our solution until we finally get to our terminating step. And that's when we end up getting two free radicals reacting together to form a new molecule, where we form a new molecule that ends up not forming any more new free radicals. Okay, which makes sense. If we have no more free radicals, they can't continue to propagate here. So these are just some terms in this section, and we're going to continue to use these throughout the next couple of lessons here. Okay. The next big term, and this is going to be the one that you're going to have to figure out and be using a lot of, is the carbocation. So often here, what is going to happen is that we're going to end up making a carbocation, and that means that it is a carbon that has a positive charge to it. And the three types of carbocations, or I guess here we have four types, are going to be defined on how well they can spread that charge out. Okay, we can have a what's known as the methyl one, and this one's less stable, which means that it's going to react really, really quickly with just about anything. The second is going to be a primary one, and a primary, the reason that it's called primary is because it's attached to one other carbon group right there. Okay. So it's attached to one other R group, which means that it can spread that positive charge out that way. So it's a little bit more stable than this one, and it continues going on down the line. So this one, notice that it has two C's attached to it, which means that it can spread that positive charge that it has around the atom itself, all the other carbon atoms, and it makes it a little bit less reactive and more stable. The last one is the tertiary, because it has three alkyl groups around it. That makes it the most stable out of all of them. Okay, and usually when we mean most stable, it means that it will be able to survive in this carbocation state long enough for us to try and get it to interact with whatever thing we want to interact it with. So typically tertiary carbon structures, when we're messing with them and trying to make something new, those are going to be the easiest ones for us to go ahead and add another alkyl group to, or to add, a halogen to, because they're in this they're the most stable of the types of carbocations. Okay, and this here is just showing the relative stability. The more R groups that you have, the more stable it's going to be. So for instance, this is a carbocation. This is a carbon that's right at the edge. It has two H's and then it has an R group on the side. Then we have a secondary one. Notice that it has two and then it has an H on the side. That's a secondary carbocation. Tertiary, it can spread its charge around all three. That's why it's called the tertiary one. The next two terms that we're going to use, and you're going to see pop up every once in a while, is an electrophile and a nucleophile. Okay, an electrophile is going to be any species in which the atom has a deficiency of electrons. So in general, if it's something that's missing an electron, it's an electrophile. Anything that has an abundance of electrons is going to be a nucleophile. Okay. And electrophiles and nucleophiles, are just attracted to each other based off of, opposite charge and magnetism. Okay. So electrophile, any species in which the atom has a deficiency of electrons, wants to bond with something of a negative charge. Nucleophile, any species of which an atom has an overabundance of electrons, wants to bond with something of a positive charge. Okay. Next, we're going to go ahead and go over the formal types of organic reactions. The first one is going to be an addition reaction. It involves the formation of a single product from two reactant molecules. This is just like normal chemical reactions. In particular here, the C2H4, the C double bond is going to end up breaking, and we're going to be able to add a bromine to both of the carbons there. Next is an elimination reaction, and it results in the removal of a small molecule from the larger one. Okay, one of the ways that we can go ahead and think about this is the dehydration of an alcohol. Notice that this right here, it ends in OH. That makes it an alcohol. And that when we go ahead and combine it with some sulfuric acid, we end up making some ethane right here, ethene, and then we end up making H2O as well. Okay, so we have eliminated that H2O. This one also will have a different type of name because, whenever we remove water, we end up saying that we're also dehydrating this particular molecule. Next is the idea of a substitution reaction. Okay, and a substitution reaction involves the replacement of one atom or a group of atoms by another. For example, whenever we go ahead and do a substitution of alkenes, it usually involves us inputting some UV light and some chlorine gas. And when we end up doing that with a methane molecule, we will end up cleaving off the bond between a hydrogen and carbon, and then we will go ahead and be able to replace that hydrogen with a chlorine there. Okay, and we'll go into this particular reaction in depth a little bit later here. Okay. Hydrolysis is going to be the breakdown of a molecule by water. This type of reaction is often sped up by adding acid or alkali, just because those are good intermediary molecules that already have a charge to them. In this particular example, when we go ahead and add water to this particular molecule, we'll go ahead and make this alcohol, and we'll end up making some hydrobromic acid here. So, hydrolysis is when we break down a molecule using water. The last one is going to be our oxidation reduction reactions. And in general, when we think about oxidation reactions, we're going to think about any reaction that usually adds a oxygen to it. Okay, and usually we'll also go ahead and say that we add an oxygen, or we remove a hydrogen from the molecule, and that's typically what we end up thinking of when we have an oxidation reaction. We add a hydrogen, we add an oxygen, or we remove a hydrogen. Likewise, with most reduction reactions, an easy way to see if it's a reduction, is if we add hydrogen, that's a pretty good sign that it's going to be a reduction reaction going on there. Okay. And in general, you can go ahead and see that in this case, this second carbon, here ends up being reduced by the oxygen, and it kicks off the hydrogen. Whereas here, this carbon right here is the one that's oxidized because it's double bonded to this carbon. Now it's only single bonded to this. This one's double bonded to this oxygen. Now it's only single bonded to the oxygen, and it has a hydrogen, which has a different electronegativity, so it feels better about sharing it right there. All right. This is going to go ahead and close us out for our types of reactions. Again, in general, remember that we have our two types. We have our homolytic, heterolytic, and then one of the big things that I want you to get out of this as well is how to identify the different carbocations based off of how many R groups are around it. Okay. But for right now, we will go ahead and close this recording out. And remember, stay lazy.